University with 5 minutes and 1 minute for questions.
Hi everyone, can you hear me? So I'm going to talk about optimization-based predictions of split belt walking. The motivation for this is that asymmetry is a common characteristic in pathological gait, like people with stroke or unilateral amputees wearing a prosthetic leg. And so we would like to be able to predict asymmetric gait. And there are rehabilitation efforts towards addressing asymmetry, different forms of asymmetry. And for instance, the split belt walking paradigm out of Amy Bastian's lab, or this, or like rehab robots like the one here, the Toyota Assist. And we would like to predict asymmetric gait. And why predict? Why build a predictive model of asymmetric gait? Well. If we were able to accurately predict asymmetric gait, then we could implement a potential proposed rehabilitation measure and then see if that would actually work, and iteratively suggest improvements in simulation, and then move on to experiments rather than doing experiments straight off the bat. So here specifically, we wanted to do a simple optimization-based predictive model for split belt walking. We've already heard one talk this week on this topic by Dr. James Finley. Specifically, what we want to predict are the observations that have been made by people like Dr. James Finley, Amy Bastian, Max Donnellan. For instance, the fact that when put on a split belt, people they spend more time on their slow leg and less time on their fast leg. That's the stance time prediction. Then we would want to predict the fact that they observe that people take longer steps on the fast belt and shorter steps on the slow belt. We would also want to predict the metabolic cost itself, because we're optimizing for metabolic energy costs, so we would want to compare the optimal metabolic energy that we find to what was seen in experiments, and also the observation that Dr. James Finley and Dr. Max Donnellan spoke about, which is that less network was done by the fast leg and more network was done by the slow leg. So the simple model that we're using here is a point mass telescoping leg model. So you have a point mass and you have a force that can, a force when your leg is on the ground, it can generate an arbitrary force. And the structure of the optimization has the equations of motion, which are written in the lab frame of reference. And the objective function that we're minimizing is a sum of the stance cost and the swing cost, where they're the energy equivalence of the work done, which is basically where you find the mechanical work and then you divide by positive and negative efficiencies. The stance cost is an integral of the force times velocity, and then we find the metabolic equivalent of that, and the swing cost is just the cost to the kinetic energy of swinging the leg from during the swing phase. And it's subject to various linear and nonlinear equality and inequality constraints, simple bounds, and one key constraint that's unique to the split belt paradigm is that the average speed has to be, the average walking speed has to be 0, because again we're on the lab frame of reference. So the first prediction that we find agrees with what's seen in experiment, which is that the stance time, that the model discovers that it spends longer stance time on the slow belt than on the fast belt, which agrees with experiments. We also predict that this stance time asymmetry would increase as the split belt asymmetry increases, meaning that if you hold the slow belt constant at 0.5 meters per second and then sweep through 0.5 to 1.5 on the fast belt, the stance time asymmetry predicted would also increase. And we're also able to predict, using this model, the observation that people take longer steps on the fast belt and shorter steps on the slow belt. Now for the metabolic energy cost, we find that, so the cost when you walk in the symmetric condition or the tight condition where both belts are at 0.5 meters per second is in the blue line, and both at 1.5, the red line that just popped up, And then both at 1 meter per second is this black line. And then what we find for the split condition is closer to the tight, slow, slow condition, which I think is an interesting observation. I couldn't find a paper that has like the actual numerical evidence for this, but just from a conversation with Dr. Finley, he says that this agrees with some of his observations. And finally, we also are able to predict the network as well. The fact that the network on the fast leg is lesser than that in the slow leg as a potential explanation for the positive step length asymmetry. So we made those predictions in experiment using the optimization-based model.
All right. We have time for one question. Amanda? John?
Sorry, could you just clarify? You were saying that you matched these like qualitative predictions. What about like numerically? Did it actually match like the degree of speed increase or whatever?
No, it hasn't. And honestly, I don't hope to match it with such a simple model.
Okay.
Typically, with models this simple, you don't tend to get quantitative matches.
So in that case, what are you going to use these qualitative matches for in terms of like all the things you were motivating with at the beginning?
Yeah, so I guess it at least points to me, it tells me that the objective function might be a good one to then put on a more complex model.
Okay.
To then test the same thing.
Okay. Yeah.
Okay, last question.
Yep. So does your model produce a unique solution for a given byte speed?
Yes.
If it's the case, do you have an idea to how to produce, people adopt on split bytes and their asymmetry changes over time?
That's a good question. I'm actually thinking about that, and one idea I have for that is to sort of, oh, okay. Yeah, so she's asking that, so we're getting these predictions for the steady state gate that people are eventually converging to, but then there's also this adaptation that people are doing, and how do you predict that? So one way to do that is some other work that I've done is on looking at variability and how variability contains information about stability. And now if you look at that variability and how it changes from step to step, maybe that contains, maybe they're just, what people are doing when they're adapting is just responding to the errors from step to step. And so if we combine this sort of a controller, like add a controller into the model and then do some kind of optimal control, then we may be able to predict the adaptation phase as well. I don't know if that was very clear, but thank you.
Okay, thanks.